Okay, in the last video, we looked at equilibrium constant and how to set up a Kc expression and how to plug in some equilibrium concentrations to solve for Kc. This video, we are going to look at basically creating what we call an ice chart. So this is something you need to do anytime you are either not given equilibrium concentrations or you're only given one equilibrium concentration, okay? So we call them ice charts, and the reason we call them ice charts is when we set them up, we're going to have initial concentration, change in concentration, and the equilibrium concentration, which is where ice comes from, okay? So how you are going to set one of these up, basically we are going to use all the chemicals that are in our balanced chemical equation, right? So you can see that our equation is 2NOCl to give us 2NO plus Cl2, which is why we're going to have a column for NOCl, one for NO, and one for Cl2, okay? And oftentimes we'll just generate that equation right below where we had our balanced equation, so we would often just have that, and then our equilibrium arrows, and then our plus. Okay, so important to make sure you're checking states just like we talked about yesterday. In this case, everything is a gas, so everything gets to go into my table. We talked about how when it comes to Kc, we're only going to include gas and aqueous because they are the only ones that have changing concentrations. So if we had something in our balanced equation that was a liquid or a solid, we would literally just draw a big X through that particular chemical within our ice table. Okay, we'll see maybe one or two questions like that in the first part of equilibrium. You're definitely going to see more when we get into the acid-base part of equilibrium. So when we are creating an ice table, really important to make sure that you remember that these are all concentration values. And that's because when we solve for Kc, we need concentration. So make sure you read the question carefully because in some cases it will give you initial concentrations, but in some cases, it's going to tell you how many moles were placed in a flask. And then you need to make sure that you're doing the moles divided by the volume so that you can get moles per liter, okay? So if we look at this question, it says calculate the equilibrium constant at 25 degrees for the reaction. So it says in one experiment, 2 moles of NOCl was placed in a 1 liter flask. And the concentrations of NO after equilibrium was determined to be 0.66 moles per liter. So write the expression for Kc, determine the concentration of each reagent at equilibrium, and determine Kc. So right now, what we are given in the question is we are told that 2 moles of NOCl was placed in a 1 liter flask. So 2 divided by 1 still gives us 2. So that means the initial concentration of NOCl was 2.00, okay? So it doesn't give me an initial concentration for NO and Cl2, and this is pretty common. And the reason it doesn't give us that is they're products. For the most part, think about when you do a reaction, you put reactants in the container, but you don't actually put any products in. So the general rule is if it doesn't give you initial concentration of products, go ahead and assume that they start at 0, okay? So next thing we need to do is we need to assign the change in concentration. So when we assign the change in concentration, we're going to use X's, okay? So some are going to get positive X values and some are going to get negative X values. And that just has to do with which way is our system going to shift to be able to reach equilibrium. So in this case, because we started, I got interrupted by an announcement. Okay, I'm trying to remember where it was. So we were talking about the change values. So they're all going to be X's, positive X or negative X. So in this case, because we started with 2 moles of NOCl and none of NO and Cl2, we know this equilibrium has to shift to the right. There's no possible option because nothing can suddenly turn into something. So because of that, both of these are going to get positive X values because we are going to be creating more of it. The NOCl is going to get a negative X value because it has to go down in quantity to actually be able to make the NO and the Cl2. So how many X's is going to depend on what did you balance with. So if you balance with a 1, it's just going to be an X. If you balance with a 2, it's going to be 2X. If you balance with 3, it's going to be 3X, and so on. So when we look here, when we go to assign the change in concentration for the NOCl, because we balanced it with a 2, this is going to be negative 2x, okay? Negative because it's the reactant in this case, and we are shifting away from it. Okay, the NO and the Cl2 are both just going to be plus x. So how we get the equilibrium concentration? It's the sum of the initial and the change. So that means for NOCl, we're going to get 2.0 minus 2x. Okay, for NO, we're going to have 0 plus x. So basically, we're just going to have x. And for Cl2, we're going to have 0 plus x. So again, we are just going to have x. So if we go back to the question, it said the concentration of NO after equilibrium was determined to be 0.66. So that's telling me that for NO, the equilibrium concentration is 0.66. So in this case, I now know that x is equal to 0.66. So because I know what x is, I now can figure out what the equilibrium is over here and what it is for Cl2. So because Cl2 is also x, it's also going to equal 0.66. Okay, then over here, we're going to do 2 minus 2 times 0.66 because we said 0.66 was the value of x. Okay, and we're going to get 0.68. Okay, so now that we've determined what all the equilibrium concentrations are going to be, we can go about actually solving for K. So ICE table always going to get you 1 mark. The next mark is always going to come from your equilibrium law expression. So we're going to write out Kc equals. So remember we talked about Kc in the last video. We said that we were going to use the concentration of products divided by the concentration of the reactants. So we're going to say it's the concentration of NO times the concentration of Cl2. And then that is going to be over the concentration of NOCl. And that needs to be squared. And the reason it needs to be squared is it was balanced with a 2, right? The NO doesn't need any little number up here because it's balanced with a 1, same with the Cl2. So we're going to have NO times Cl2 divided by the concentration of NOCl2 squared. So we are going to have our 0.66 times our 0.66 because those were the equilibrium concentrations of the NO and the Cl2. And then that is going to be divided by that 0.68, which is going to be squared. Okay, so things to watch for. Sometimes you guys will write the square here and you get to here and you lose the square. Or you'll write the square here and then you go to your calculator and you lose the square again. So really important to make sure that you are looking, I guess I would say, at the small things and not ignoring them, because that tends to be the biggest mistake you guys make. You'll have everything set up right, but then you have issues either plugging it in your calculator or you lose something, okay? So significant digit wise, we get to have 2 significant digits because we had 0.66 as the given equilibrium concentration. So we calculate this, we get 0.94. Okay, if you think about that, that should make sense, right? That's really close to 1. I would expect this equilibrium to have a K pretty close to 1. And the reason for that is, remember we said the other day that equilibrium concentrations are approximately equal. Well, look, 0.68, 0.66, and 0.66. Those are all very close together. So it's not very surprising that I have a Kc pretty close to 1, okay? So let's try some more examples. So we have 4 HCl plus O2 to give us 2 H2O and 2 Cl2. So we have 6 moles of HCl and 2 moles of O2 are placed in a 1 liter container. When equilibrium is established, 2.40 moles of water are present. What is the equilibrium constant for this reaction? Okay, so what we need to start by doing is creating that ICE table, right? So we have 4 HCl. Okay, it's a gas, that is good, that means I can use it, plus O2, also a gas. Just tab that out a bit. Then we have 2 waters, again a gas, so it gets to stay, plus 2 Cl2, again, also that gas, okay? So, double-headed arrow, and then we can go ahead and create that ICE chart. So, that, and that. This takes a while. Okay, of course I'm going to have not made my lines big enough, but we'll just pretend they are. Okay, so here is going to be the initial, the change, and the equilibrium values, okay? So 6 moles of HCl in a 1 liter flask. So the initial concentration of this is going to be 6 moles per liter because it is a 1 liter flask. Okay, oxygen, we are told 2 moles in a 1 liter flask. So again, this is just going to be 2. Okay, we weren't given any info for the water or the Cl2. They're products, so we are safe to assume they are going to start at 0. Okay, so because our product started at 0, this has to shift towards the right, which means both of our reactants are going to get negative X values and both of our products are going to get positive X values. So for the HCl, it was balanced with a 4. So this is going to be negative 4X. Okay, the oxygen was balanced with a 1, so just negative X. Get over to the product side, so we're going to switch the sign over to a plus. So the water has a 2, so this is going to be a plus 2X. And the Cl2, same thing, it has a 2, so it is also going to be a plus 2X. Okay, equilibrium, same as before, we're getting the sum of this. So we're going to get 6 minus 4X. And here we're going to have 2 minus X. Here we're just going to have 2X. And then same with the last one. We're going to have 2X because, again, 0 plus 2X is equal to just 2X. Okay, so when equilibrium is established, 2.40 moles of water are present. So we now know that this 2X is going to equal that 2.4. I'm just going to maybe change colors so it stands out. Okay, so I now know that 2X equals 2.4. In this case, that is going to represent my equilibrium concentration of water. What I do want to do, though, is figure out what X is actually equal to so that I can sub it into all of these other ones, right? For Cl2, it's not super important because it's 2X, which is exactly the same. So I already know that this one here also has to equal 2.4. But for the other ones, it's helpful to figure out what X is actually equal to. So if we have that 2X equals 2.4, we know that X has to equal 1.20 because 2.4 divided by 2 is equal to 1.20, okay? So now that I know what X is, I've already figured out the equilibrium for the Cl2 and the water. We can now go in and figure out what it's going to be for the HCl. So we're going to do 6 minus 4 times 1.2. And we got that this is going to equal 1.2. And the other one, we get 2 minus X, so 2 minus 1.2. And we come up with 0.8. Okay, so now we have our isotable created. We've determined what all the equilibrium concentrations are. Now we can go ahead and set up our Kc expression. So we are going to have that Kc is equal to, so it's going to be our product, so concentration of water. It's not looking right. Hold on. Water. And that is going to be squared, and it's squared because we balance the water with a 2. And then it's going to be times the concentration of Cl2. And that's also going to be squared because it was also balanced with a 2. Okay, now we're going to divide by the concentration of HCl. And this is going to be to the power of 4 because we balance with a 4. And then finally times the concentration of oxygen. And this isn't to the power of anything because it was balanced with a 1. Okay, so we wind up with water squared times chlorine squared divided by HCl to the 4 and divided by oxygen. So once we have that, go ahead and plug our numbers into this. So we're going to have our 2.40 squared times 2.40. I'm hitting the wrong buttons, squared. And then that is going to be divided by that 1.20 to the 4 and 0.8. All right, so now let's plug this in our calculator, see what we get. So 2.4 squared times 2.4 squared divided by 1.2 to the 4 and divided by 0.8. We come up with 20. Okay, so calculator said 20. But when we start looking at all the given numbers, this had 3 significant digits, this had 3 significant digits, this had 3 significant digits, this had 3 significant digits. Okay, we do also want to be mindful, however, of the fact that we did do some subtractions in here, right? So why that's relevant, remember we have different rules for subtraction than we do for multiplication and division. So in this case, I only wrote this as 0.8, but really it does have that additional 0 at the end because it was 2 numbers after the decimal place, so there would still be 2 numbers after the decimal place. So technically this question should have 2 significant digits because this 0.80 was used in my calculation. Okay, however, you will find that we tend to be pretty lenient-ish with significant digits. If you would have given me 3 significant digits for this question, based off the fact that everything in the question had 3, I wouldn't have docked you for significant digits on this question. Okay, so either 20 or 20.0. Technically 20 is the more accurate one because we had this operation leading up, but either works. Okay, so this is kind of your simplest ICE table. It's going to give you some initial concentrations and then it's going to give you one equilibrium concentration, which then allows for you to determine what everything else is at equilibrium based off of that ICE table. So this question is a little different. Okay, this one, instead of giving you an equilibrium concentration and asking you to solve for Kc, this is giving you Kc and asking you to solve for the equilibrium concentrations. So our general processing on a question like this isn't really going to change. It's still going to be the same. It's just going to be when we get into that Kc calculation, it's going to look a little different. So we have the following reaction shows one of the possible reactions between carbon monoxide and water. So we have CO plus H2O to give us H2 and CO2. Okay, everything is a gas, so we're going to use everything. So at 700 Kelvin, right, it's giving us a temperature. The reason these questions give you temperature is if you remember in the last lesson, we talked about how K is dependent on temperature. That's why they give you temperature, not because you're using it in the calculation, simply because I could give you the exact same reaction, but give you a different temperature and it would have a different numerical value of Kc. Okay, so at 700 K, the Kc is 0.83. If you start with 1 mole of each reactant in a 5-liter container, what amount, maybe I'll just change that to say what concentration of each species will be present at equilibrium, right? Amount's not super specific. It could be talking moles, it could be talking concentration, so let's just make it concentration. So starting point, we are going to start by writing out that equation. So we have our CO plus our water to give us hydrogen, carbon dioxide. Have some stuff out a little. Okay, so everything balanced with a 1. We are going to create our ICE table. All right, so this question's a little different. The reason it's a little different on a different note is because this is a 5-liter container. All the other ones we've looked at have all been 1 liter. This is a 5-liter. So I shouldn't ever assume that it's always a 1-liter container because it isn't always going to be a 1-liter container. So we were told 1 mole of each reactant in a 5-liter container. So we have to do moles divided by liters. So 1 divided by 5 so that we can get the initial concentration of these two. Okay, so they wind up being 0.20. 0.20. Okay, again, we're not given any info for our products, so safe to assume they are 0. Okay, change value-wise, because I'm not starting with any products, it has to shift to the right. So this is going to be negative x. Okay, and just 1x in this case because everything is balanced with the 1. And then both our products are going to be plus x. All right, so now we got to figure out our equilibrium. So we're just going to basically get the sum of our initial and change. So we're going to go 0.20 minus x. This one is also going to be 0.20 minus x. And then these ones, 0 plus x is simply x. And same thing here. Okay, so all of this is the same as where you started with the last two questions. The difference is I don't know what any of these equilibrium concentrations are. So I can't actually figure out what x is right now. I can do it, but I can't do it right now, okay? So next thing we're going to do is we are going to set up that Kc expression. So we're going to have that Kc is equal to the concentration of hydrogen times the concentration of carbon dioxide, and that's all going to be divided by the concentration of carbon monoxide and water. Okay, so all the other ones we plug numbers into here. Now we're not going to plug numbers into here. Difference this time is I actually know what this number is. I didn't know that in the previous questions, right? You can never have more than one unknown and actually solve a question unless you have additional information or additional equations. So what's going to happen here is I know Kc. The question gave it to me as 0.83. So we're going to have that 0.83 is equal to, so we're going to plug in these values that we have for equilibrium for H2, CO2, CO, and H2O. So we're going to get x times x. And that's all going to be over 0.20 minus x times 0.20 minus x. So this particular question, I can do something that's going to make my life much easier to actually solve this. And what I can do is if I look at this, I should be able to recognize that x times x is the same as writing x squared. And 0.2 minus x times 0.2 minus x is the same as writing 0.2 minus x squared. So let's get rid of that and square that. And then let's do the same on the bottom here. So why did I want to do that? Okay, the reason I wanted to do that is if this is squared and this is squared and this is a number, I can take the square root of both sides. Why would I want to do that? Well, because otherwise I'm going to have to use quadratic or I'm going to have to graph this to attempt to solve for x. But if I take the square root of both sides, then what I can do is I can say the square root of 0.83. I'm just going to leave it as square root of 0.83 right now because the square root of 0.83 is a gross messy number. And I don't really feel like dealing with a gross messy number and writing it all out. I'm probably going to wait till the end in my calculation to actually figure out what that number is going to be. So if I take the square root of x squared, that is simply x. And if I take the square root of 0.2 minus x squared, that's just going to be 0.20 minus x. So now I've made this a much simpler equation to solve because I just have some x's and I don't have any x squared. So I'm going to have to multiply these two together, right? Eventually I have to be able to solve for x. So we are going to say that we have, let me see if I can find a symbol. Oh, look at that. There is a symbol for square root, maybe. Or maybe not. Yeah, okay, I'm just going to draw. That's going to take too long. So we are going to have the square root of 0.83, and that is going to be times that 0.20 minus x, and that is going to equal x, right? So we took this term and we moved it over to this side. Okay, now we have to multiply this through. So this is where I'm going to have to actually figure out what is the square root of 0.83. So we're going to do square root of 0.83 times, hold on, it's doing it all under, times 0.2, right? So taking this and we're multiplying it by this. So square root of 0.83 times 0.2, I get a lovely, beautiful number because that is chemistry. I get 0.1822, and that number just kind of keeps going on. I'm just going to put dot, dot, dot because I don't want to write the whole thing. Okay, and then it's going to be minus because it's minus x. And so remember, we have to do that square root of 0.83 times x. So again, square root of 0.83. We're going to have 0.911. And again, that number keeps going. X equals x. So just like in math class, when you are trying to solve for x, we need to isolate x. So the x that's currently right here needs to move over to this side. So because it's currently minus x, when we move it over to the other side, it becomes a plus x, right? So we're going to take this, and we are going to move it to this side. I don't think I highlighted that right. So we wind up with that. Okay, now we need to combine these two together. So we still have that 0.1822 is going to equal, so x plus 0.911x is going to be 1.911 x. Okay, so once we have that, to isolate x, we need to divide both sides by that 1.911. Being difficult, come on, computer. And then from there, we can figure out what x actually is. So you do have to be careful in that you don't want to lose numbers, right? So the unfortunate part of when we do this in chemistry is it's not like when you do this in math and you have these nice pretty numbers. You have, when you look at your calculator, kind of some gross numbers. So I know sometimes what some of you like to do is you like to, once you have that number, kind of say, program it in your calculator, be like, oh, this number is going to be A and this number is going to be B, and then it can make it a little bit easier because it will carry all the numbers through. It's kind of up to you what your level of comfort is, I guess I would say. So let's do this operation. So we're going to do that 0.1822 with all those other numbers at the end. We're going to divide by the 1.911 with all its numbers at the end. And then we should be able to solve for x. So you should be getting 0.0953, and then that keeps going. Okay, so now we have solved for x. Now that we have x, we can go back up to our ICE table, and we can figure out what these equilibrium concentrations are going to be. So because hydrogen and carbon dioxide were both just x, we now know what their concentration is going to be, right? Because we just solved for x. So this is going to be 0. Oh, hold on, that's not where I want to type. This is going to be 0.095. Make sure you don't forget to throw a unit in, right? You can either write moles per liter or you can put the capital M in. Okay, and then this is also the same, so it's also going to be 0.095. But I changed the color. Apparently I only changed it for the one. Okay, and then these guys over here, now it's finally set to red, are going to be 0.2 minus x. So we can do 0.2 minus the x value on our calculator. So we wind up with 0.10 moles per liter for both of these. It's not doing what I wanted it to do. All right, 0.10. So these questions are more work. There's no doubt about them. They take more time. They take more comfort with your calculator and being able to solve for x, okay? So significant digits, this got two numbers after the decimal place because I was doing a subtraction, so hence two numbers after the decimal place. This one here, simply based off the fact that everything I was given had two significant digits, that's why it was allowed to have two significant digits. Okay, in this case, for our products, it's not about decimal places because they were simply equal to x. So you do find that the sig-dig rules between the reactants and the products are a little bit different because we did a subtraction with one and we didn't with the other. Okay, again, usually pretty lenient with that as long as you're not like crazy with your significant digits. Usually it is a-okay. Okay. So one thing you can definitely do on a question like this once you get to the end, to make sure that you've actually solved it right, is plug those equilibrium concentrations back into your Kc expression to make sure that you get something that is close to the actual KC. Okay, you may not get an exact perfect match, and that's because we've rounded for significant digits through the question, but usually you're going to get something that's pretty close. If you find that you plug into it and you get a number that is entirely different, it's usually a pretty solid indication that you made a mistake somewhere in your calculation. So maybe you lost a square, maybe you missed a step, and that would be when you want to go back and double check for it, okay? All right, so let's look at this one. So we have PCl5 to give us PCl3 and Cl2. So again, let's write our equation. Oops. Okay, so we have that. We have our arrow. Okay, we're setting up our ice table just like we did in the last few questions. All right, so from here, 1 mole of PCl5 is placed in a 2-liter flask. So 1 divided by 2 is 0.5. So the initial concentration is going to be 0.500. Okay, we're not given any initial information for the other two, so they are both going to be 0. Okay, change values, PCl5 is going to be minus X, and the other two are both going to be plus X. Okay, so equilibrium is going to be 0.5 minus X, X, into X. All right, so same as the last example. We're not given an equilibrium concentration, so we are going to have to go right into that Kc expression. Again, we are given Kc, so that's okay. This is still a solvable question. So we have that Kc equals the concentration of PCl3 times the concentration of Cl2, and that's all going to be divided by the concentration of PCl5. And apparently I missed my equal sign in here. There we go. Okay, so next thing we're going to do is we're going to plug some numbers and x's into this. So we were given the Kc as 3.60. This is going to be equal to x times x, and that's going to be divided by 0.5 minus x. Okay, I'm going to lose those zeros for now just so that there's less written in there, but they are still technically there, okay? So this is different than the last question. The last question I got to take the square root of both sides, and I could do that because I had an x squared on the top, which I still do, but this was also squared on the bottom. So I don't get to do that this time. So you have options of how you can approach this question. Most of you at this stage usually choose to graph this and solve for the x-intercept, just like you did in math last year when you were in the quadratics unit. Some of you may choose to do the quadratic formula, which is also a doable thing, right? We would have to move this over to here, do the 3.6 times 0.5 minus x, expand that out. This would give us our x squared. If we were doing the quadratic, we would set it up in that 0 equals, and then we'd have the x squared, the x, and then the thing without the x. You will find that if you go to your data booklet on page 3, it does give you the quadratic formula right in here. So if you are choosing to do that, it is provided to you. It is given to you. I don't want to say I don't recommend doing that, but I find in general you guys are way better at solving for x on your calculator than you are at successfully performing the quadratic equation. So again, it's kind of up to you. In class, I can help you walk through some of this stuff. It's a little hard to do this in a video. I know some of you guys have Casios, some of you guys have TIs. Again, it's going to look a little different with how you go about doing that. But yeah, so go ahead and either set this up for the quadratic or set this up within your calculator exactly like you did in math class. So I have a TI, so I could show you how to do it on a TI. If you don't have a TI, then sorry, I can't really help you because I don't actually have a Casio sitting in my room. So I am going to hit this little Y plus button that's right up here. It's going to bring up Y1, Y2, Y3. So how I'm going to enter this is I tend to enter all of this as my Y1 value. So although it's written as X times X, I'm just going to put that in as X squared. Okay, then I'm going to divide by, and then I'm going to put all of this into brackets. So 0.5 minus X, and I'm going to close my brackets. Okay, so that's kind of what that first line is going to look like. So I have my X squared, and then I'm dividing by, and then inside of brackets, 0.5 minus X. Okay, then I'm going to go to Y2. Y2 is where I'm going to plug in that 3.6. Okay, so now I've got all of that plugged in on my calculator. I'm then going to hit the graph button that's over here, and that is going to go ahead and generate that graph for me. Okay, once it's done generating that graph, I am going to ask it to solve for the x-intercept. So I'm going to hit the second function, and then I'm going to hit the calc button. Okay, it should bring up a list of options. From here, number 5 says intersect. I'm going to choose number 5. So at first, down here at the bottom, it says first curve equals 0. I'm going to hit enter again. I was going to say second curve, x equals 0. And then I'm going to hit third curve, or enter again. Oh, it didn't work. I lied, it did work. I just apparently didn't actually hit the enter button the last time. So it then is going to tell me, you can see, it gives me that intersection right there down at the bottom of the screen. So from here, I figured out what my x value is. So I get that x is equal to 0.44499, and it keeps going, okay? Different calculators look a little different. I know the Casio works similar, but slightly different. But yeah, so in class, we can kind of walk through some of these examples a little bit more. It's kind of hard in a video when I only have the TI to show you how the Casio works, okay? But yeah, so now that I have X, then I can go back and I can plug that into this question. Okay, so the one thing I do want to point out with a question like this, I don't need to see all your work from how you got to here to how you got to here, because I know a lot of you do it in your calculator. However, if you are choosing to do the quadratic and you need to write all those steps out, by all means, please do write all those steps. Okay, however, when it comes to marks, there's a mark for your ICE table. Okay, there's always a mark for that. There's a mark coming from your Casey expression. There's a mark from numbers being plugged into your Casey expression. And then there's a mark for X, and then obviously the last mark comes from having that final answer. But you'll notice there's no mark for all the work that comes between here and here. Okay, so if you want to write it, you can write it, but really the important thing is, can you actually get what X is out of something like this, okay? So really important to make sure you know how to do that on your calculator if you are choosing the calculator route, okay? I've definitely seen some of you guys be like, oh yeah, I'm good. And then you get your KC quiz and all of a sudden you're like, I don't actually know how to get an X out of my calculator. So really important to make sure that you are practicing to be sure that you can get it, because nothing sucks more than basically being able to do everything except use your calculator, okay? It's a tool, but it only works if you actually know how to use it, okay? So now that we figured out what X is, we can go ahead and figure out what our equilibriums are going to be. So significant digits, we can have 3 for these ones. So we're gonna have 0.445 moles per liter and 0.445 moles per liter. Okay, and then for the other one, we're going to do 0.5 minus 0.44499, and then all those other numbers that come back. So because this is a subtraction, we get to have 3 numbers after the decimal place, so we get 0.055. Okay, again, probably a good idea to double check in your calculator that you've actually solved properly. So how I'm going to do that, I'm just going to take these numbers and I'm going to plug them back to KC. So I'm going to do that 0.445 times 0.445, and I'm going to divide by 0.055, and I'm getting that 3.60. So I know that I've solved this question correctly. Okay, so this is how you do ICE charts. Some people need a lot of practice at this. Some people need a lot less practice at it. Really what it comes down to is your ability to solve for X, right? Some of you are super confident in your math skills, and this is going to be a really nice, easy, straightforward thing for you. And some of you are like, math is not my strong point, and you are going to find that you are going to have to spend a lot of time practicing these. So really important to make sure you understand how to do these, because we're doing more of this tomorrow, and we're doing more of this once we get into the acid-base part of equilibrium. So these calculations aren't really going anywhere. They're going to be with us for the next month or so. Okay, so important to make sure you can do it. If you can't do it, make sure you come see me.